Hey class, this is Adrian Seaver again. We are here to discuss section 4.3. We just got back a little while earlier from our class tonight. Hopefully it went well. I enjoyed being back in the classroom and kind of seeing some faces and getting to know you guys a little bit. So we've got a couple videos under our belt, so I wanted to dive right into section 4.3. This section will probably be assigned while I am away next week, but I also wanted to provide this just kind of as a video that would help either way. We'll probably come in and review this a little bit when I get back from my trip, but I did want to go ahead and cover this topic. So in the last section in 4.2, we discussed a little bit about defining our trigonometric functions, sine, cosine, tangent, etc., under the auspices, I guess you would say, of the unit circle. So we said, all right, the sine of an angle, if you look on the unit circle, is going to equal the y coordinate of the point on the unit circle. The cosine of the angle at a point would be represented by the x coordinate of that point on the circle. So another way we can define these trigonometric functions is through right triangles, and we're going to talk about that. This is actually my preferred method. I don't know why. I guess this was the way I was taught, so I really kind of enjoy this type of method. But trig is used a lot, as far as angles and circles like we talked about. It's also used extensively in just looking at triangles, navigation and building, other applications that we're going to see, throughout this class, and hopefully you'll see in other classes throughout school and through your career. It says, consider the angle pi thirds on the unit circle as examined in the last section. Now construct a right triangle. So I'm going to very briefly do that. It might not be quite to the level that I would do, in class, but I did want to touch on that. Let me put some lines in here so we can see this a little bit. So if I have a 60-degree angle, and if you remember correctly, we come in here and we've kind of got our standard coordinate axes, and again our initial side is going to be here on the x-axis. That's kind of our 0. So as we go up to 60 degrees, let's just oops, I didn't do that. Let's go 60 degrees here, and we'll kind of pretend at least that's on our unit circle. So that would mean anyway, so here's our angle, 60 degrees. We're coming up here. So then the last time we said, all right, let's use the end point there on the unit circle and use the coordinates of that point to determine, sine, cosine, tangent, etc. In this section, we're going to do something a little bit different. We're going to take that point, and it doesn't have to be unit circle, or it doesn't have to be radius 1, but we're going to take that and we're going to say, well, let's drop a perpendicular line from that point down to the x-axis. So if we were to do that, here's our point, right? Let's see, for some reason it keeps popping. There we go. That would be, let's call this point x comma y, right? So in the last segment, when we were in the unit circle, so well, sine would be y, the cosine would be x. In this case, if we think about what x and y really represent at any angle, any length radius, this point would have x coordinates, so this side of our triangle would have a length of x, and the y would be right across here. That would be the length of this side then. This opposite side in this case would have length y, and then this line segment here is going to be our radius. If it's on the unit circle, that'd be 1. So that's kind of drawn out here. You can kind of see over on the left-hand side here, back on our handout, you can see we've got x and y and kind of got this all drawn out on a unit circle definition. And we're going to define sine, cosine, tangent, etc. Instead of using, the unit circle, we're going to say based on the lengths of the sides of this triangle. So if you go back to geometry and you start thinking about similar triangles and how those lengths are related and how those ratios have to equal for any, however big the triangle is, if the angles are equal, then the ratios have to equal out. So without going into too much detail, what I wanted to point out is for sine of theta, sine of any angle theta, if you look at the opposite side length of your angle divided by the hypotenuse, which is the longest side of your triangle, which is always the side opposite the 90-degree angle that you've kind of sketched out here, then that's going to be defining the sine of your angle. Cosine is the adjacent side divided by the hypotenuse. So this picture that I have on the handout here, your sine would be opposite over hypotenuse, which would be A over C. Your cosine would be B over C, or adjacent over hypotenuse. And then tangent is opposite over adjacent, which kind of makes sense, right? Because we said last time tangent is sine over cosine, and that's the way it works out again here. So really what it comes down to, and probably the easiest way you're going to remember kind of these ratios for sine, cosine, and tangent is through the term SOHCAHTOA. Now, there's different ways to remember that. A lot of people have different ways. My favorite way is some old Hokies came around here, took out Alabama. So that's the way I remember it. You probably have other definitions, but I like that one. I'm a little biased. So another one I've heard, I think, is saddle old horses, canter away happily to other adventures. So if you have another good way to remember SOHCAHTOA, let me know. It'd be kind of interesting. I've heard one or two through the years, but anyway. So let's use this SOHCAHTOA, this right triangle definition, and this is going to be used on any right triangle. It doesn't have to be, a unit circle or a point out here on a circle in a coordinate plane. Any triangle that is a right triangle, meaning it has a 90-degree angle, is going to obey this SOHCAHTOA law for sine, cosine, tangent, etc. So as I come in here and I look at my first example, it says find the value of the 6 trigonometric functions of theta. So here's my angle theta. If I wanted to find the sine of theta, that's what's going to be, right? Sine is opposite over hypotenuse. So the opposite side of theta is this A equals 3. So I'm going to have 3 over, and then the hypotenuse, again, that's the longest side, but it's also the side that is opposite your 90-degree angle. And it's always going to be your longest side. Now, here, I only give you the opposite and adjacent sides, so we got to figure out how do we find this hypotenuse. Well, if you go back to geometry and other classes, probably algebra as well, you found out that for right triangles, you have what's called the Pythagorean theorem. So you have a squared plus b squared equals c squared. Now, I've labeled it that way conveniently, so that works out well. But again, this c in a squared plus b squared equals c squared, that has to be your longest side. That's the way this is defined. It's also the side opposite your 90-degree angle. So let's go in and figure out, based on this triangle, what these a, b, and c are. So we're given a is 3, so I'm going to say 3 squared plus, and then b is given as 4, so 4 squared equals c squared. So we need to solve this for c. Well, I'm going to square these terms over here first. So 3 squared is 9, 4 squared is 16. So that equals c squared when I add those. So 9 plus 16 is 25 equals c squared. So then from here, you're going to take the square root of both sides, and algebraically, you're going to say plus or minus the square root of 25. But we don't have to worry about the negative 25 because we're representing this as a length. So since we're measuring a length, we're not using negative lengths or distances. So we're going to go ahead and only use the positive here. So the square root of 25, and I'll write that in here, which is 5, is going to equal c. So now we know the lengths of all the sides of our triangle. So I can come in here and say, well, the sine then would be 3 over 5, because that's the length of our hypotenuse. Cosine, here's theta. The adjacent, that means it's touching the side of theta, but it's not this longest side, this C side, or this hypotenuse side. So we're going to say the adjacent side is 4, so 4 over 5. And then the tangent of theta is the opposite. I'll switch colors here. The opposite over adjacent, so it would be 3 over 4. Now, if you go back to last section and just kind of in general, you go to our reciprocal kind of rules, you got 3 over 5 for sine, so that means cosecant would be the reciprocal, or it would be that flipped, so it would be 5 over 3. The secant would be this one flipped, so it would be 5 over 4. And the cotangent would be 4 over 3. Okay, kind of neat. So that's pretty easy, I think, as far as defining it that way. And this one, we had nice even, good, round, whole numbers. Let's look at one a little bit different. In the next example, it says find the value of the 6 trig functions of theta in this figure. So this one's a little bit different. Here, C equals 5. Notice that is the hypotenuse. That's our longest side, but we don't know what B is. So let's determine that first here, and then we can go in and kind of use our rule. So we're going to use the Pythagorean theorem again because it's a right triangle. And we're going to say, all right, 1 squared plus B squared equals 5 squared, okay, based on that triangle. So we're going to have 1 plus B squared equals 25. Okay, so that looks good. So let's subtract 1 from both sides because that's what we're going to solve for this B squared. So we're going to have B squared equals 24. And then we'll take the square root of both sides. So we're going to have B equals square root of 24. Well, this one's a little bit different, right? Because we can't take it's not a perfect square. I can't just take the square root of 24, but I can simplify this down here. So I did put that in the instructions here. So we're going to simplify that. We can come in here and say, well, square root of 24, that's the same as the square root of 4 times 6, right? Well, the square root of 4 is 2, so I can pull that out of the radical sign. So I have 2 times the square root of 6. So that's the length of this side B, 2 times square root of 6. So now that I've got my side lengths, it's easy enough to come in here and say, all right, the sine of theta is going to be equal to the opposite over hypotenuse. So the opposite is 1, hypotenuse is 5, so we're going to have 1/5. The cosine of theta is going to be the adjacent side, 2 times the square root of 6, divided by 5. So that's good. And then the tangent, we'll have to think about this one a little bit. We've got tangent of theta equals the opposite side over the adjacent side. So we're going to have 1 over 2 times the square root of 6. Now, last time we talked about this, you are not supposed to, and the homework will agree here, leave that radical sign in the denominator. So that means I need to multiply the denominator by whatever that radical is. I just multiply by that. So I'm going to say multiply the bottom by the square root of 6. If I multiply the bottom, I also have to multiply the top. So I'm going to multiply this whole thing by square root of 6 over the square root of 6. So when I do that in the top, I'm obviously going to get square root of 6 because that's 1 times that. On the bottom, it's going to be a little bit different, right? The square root of 6 times the square root of 6 is 6. But don't forget you got that 2 down here, right? So I'm going to have 6 times 2, which is 12. So that should be your tangent in this case, is square root of 6 over 12. Okay? Okay, so let's kind of move on. We'll come back to these answers. Let's look over here at our cosecant of theta. Again, we're going to flip signs, so it would just be 5 over 1. The secant of theta, this is another one we're going to have to simplify a little bit. Secant of theta would be 5 over 2 times the square root of 6. So we're going to do what we did last time. We'll multiply top and bottom by square root of 6. So that's going to give us 5 times the square root of 6 in the numerator. On the bottom, we would have square root of 6 to square root of 6. That is 6 times 2 again, so we're going to have 12. And then finally, for the cotangent, we're going to flip the tangent. And then rather than flip this one, remember we talked last time a little bit about this. We have 2 potential solutions, only one's in the correct form. But we can take this original form, 1 over 2 times the square root of 6. If I flip that one, I'm good to go, right? So I'm going to have 2 times square root of 6 over 1. So that's your answer. If you flip square root of 6 over 12 and simplify it, you're going to get to the same answer. But sometimes it's helpful to have that other option that you can flip around. So anyway, so let's move on. That's pretty good. That's a summary of how we can do this with triangles. Next here it says last section, you may remember this if you've watched the last section, we discussed how to find the trig identities for a 45 degree or a pi over 4 angle. Now you can similarly do that using right triangles as opposed to the way we did it last time where we kind of used the definition of the unit circle and figured out, hey, x equals y at this point, et cetera, et cetera. So in this one it says, all right, if a triangle has angles of 90 degrees and 45 degrees. So let's come in here and just kind of sketch this out. So here's my coordinate axes. I'll draw all these out here, right? So here's my initial side. Actually, I'll switch colors. Maybe this will make more sense. So here's my initial side, right? My terminal side is going to be at a 45-degree angle. This might not be perfect, but we'll say it's close enough, right? So 45 degrees right here, right? Okay, so if I pick any point, like I said, it doesn't really matter. But if I pick any point, let's say this point, and I bring down this perpendicular here to the x-axis, then I have a 45-degree angle in this triangle, and I have a 90-degree in this triangle. What does this other angle have to be? Well, if we were in class, we'd discuss this, but all the angles in a triangle have to add up to 180. So if I take 180 and I subtract out this 90-degree angle, and then I subtract out this 45-degree angle, then that's going to give us what this other angle has to be, right? So 180 minus 90 is 90 minus 45. And 90 minus 45, guess what? 45 degrees. So that means this angle as well is also 45 degrees. So we're just kind of setting this up, what this looks like. So given that this is an isosceles triangle, right? So we have two equal angles and two equal sides, right? So this x and y have to be equal, right, for a 45-degree triangle, and those two angles are equal. And what that tells us is that if we give a value to these equal sides here, in our case, this is our adjacent side, I guess, to 45 degrees, and this would be our opposite side, then we can figure out what the length of the other side is going to be. So let's come in here and let's say, all right, let's say adjacent side, let's set that equal to 1, for example. And let's say our opposite side is also equal to 1. Okay? Because they have to be. It's a 45-degree angle, and it's an isosceles triangle. So what would be the length of our other side, or our hypotenuse here? Well, you'd come in here and you'd say, well, hypotenuse squared has to equal a squared plus o squared in this case. So we're going to say h squared equals, well, 1 squared is 1. So plus 1 squared again, so 1. So we get h squared equals 2. So then h is going to be the square root of that, right? Square root of 2. Okay, so that's interesting. We have a triangle here done a little bit differently. And so based on this triangle, if you come in here, we've got 3 sides of this 45-degree angle, right? We've got 1 and 1, that's our opposite and adjacent side, and then square root of 2 for our hypotenuse. So using SOHCAHTOA, we can come in here and say, well, all right, the sine of a 45-degree angle, or pi over 4 radian angle, same difference. The sine of a 45-degree angle would be opposite over hypotenuse, so that would be 1 over square root of 2. And if you go back here, you simplify that. In the last section, we did this as well. That's the square root of 2 over 2. So that is the sine of a pi over 4 radian, or a 45-degree angle. Cosine of pi over 4, just write it differently this time, is also going to be, again, adjacent, which is 1 over square root of 2, which is, again, square root of 2 over 2. Now, same results that we got last section when we did it a little bit differently. So finally, we come in here to tangent of pi over 4. And we're going to come in here and do the same thing. We'll say opposite over adjacent, and we find out that is 1. Okay, so we know the sine, cosine, tangent. We can relatively quickly find the cosecant of 45-degree angle. We're going to take this 1 over square root of 2, we're going to flip it. So it's going to be square root of 2. The secant of 45 degrees, or pi over 4. We're going to take our cosine here, flip it, right? So instead of 1 over square root of 2, we're going to flip that. It's going to be square root of 2 over 1. And tangent's easy enough. If tangent is pi over 4 is 1, then the cotangent of pi over 4 is 1 over 1 flipped. So it's still 1 over 1. So it's still 1. Okay? So this is just another way of defining these 45-degree, this kind of a special angle. We'll come back to this a little bit. Another series of special angles we're going to talk about are 30 degrees and 60 degrees. So to kind of derive those using triangles, we're going to do it a little bit differently. We're going to say, all right, let's take an equilateral triangle, right? So every angle is 60 degrees. So here's a 60-degree angle. There's another 60-degree angle over here. And then this top one, right? That's also 60 degrees. If it's equilateral, the angles are equal and the sides are equal. So given that triangle, if I come up here and I bisect this angle directly in the middle, I'll switch colors, then that makes half of this angle, 60-degree angle, then that's my 30-degree angle, right? And I draw that down to the base here, and you'll see that's going to make a 90-degree angle. That's how these bisectors are kind of drawn here. So you'll see that if I let this each side, now there's a reason, I guess the reason behind this is I get two whole numbers here. So if I let each side of this original equilateral triangle be 2, I'd have length of 2 here, length of 2 here, and the length of 2 here. Well, when I come down here and I cut this in half, right, I'm going to meet at the midpoint of this baseline. That makes this length half of that 2. So I'm going to have 1, 2, and then again, kind of like we did last time, we can figure out what this other length side is going to be based on this definition. So I could come in here and I say, well, my hypotenuse, right, opposite this 90-degree angle, that's 2. So I would have 2 squared equals 1 squared plus, and we're going to use 60 degrees here, so I'll label this for now as, I don't know, B, whatever. So I'll label that as B. So plus B squared. So that gives us 4 equals 1 plus B squared. Subtract 1 from both sides, you get 3 equals B squared. Square root of both sides, you get square root of 3. So I have a 60-degree angle here, and I know the lengths of all 3 sides of that triangle. So as I come in here and say, all right, find the, well, I'm gonna do the 60 degrees first. So it says find the cosine of 60 degrees. Well, the cosine of this 60-degree angle would be the adjacent side, which is 1, divided by the hypotenuse, which is 2, right? That's our longest side, opposite the 90. Okay. Now notice here I also say find the sine of 30 degrees. Well, that looks a little different because right, this is our 60-degree angles down here along the base, so it looks a little bit different, but it's the same concept. If I come to this 30-degree angle and I say, all right, I want to know opposite over hypotenuse. So the opposite of that 30-degree angle is 1, and the hypotenuse of still 2, right, longest side. So tangent of 30 degrees, that means I'm basing it on this angle. So the opposite of that angle is 1. And over the adjacent side, so the adjacent side to 30 degrees here, keep in mind, is this side right here. Not the 2, that's a hypotenuse. So it's going to be the square root of 3. So it'll be 1 over square root of 3. Simplify that down, it becomes square root of 3 over 3 when you rationalize that denominator. And then finally, for tangent of 60 degrees, it's going to be opposite, which is square root of 3, divided by the adjacent side, which is 1, so it's just square root of 3. Okay, so last time we discussed a little bit all these different angles that we're kind of building up our knowledge of. So you could come in here and kind of look on your coordinate axes and unit circle or whatever, and you can kind of say, well, I kind of know everything now. I know what I need to know at least about a 0-degree angle or a 0 radian angle, which is equivalent to a 360-degree angle or a 2 pi radian angle. And I know those values. I know sine, cosine, tangent, right? And the way I remember those is actually through the unit circle definition, because this point in the coordinate system on the unit circle would be the point 1 comma 0, which is, right, that's your cosine and sine. So the sine of a 0-degree angle is 0, the cosine is 1. I also know 90 degrees, right? I know 180 degrees. And you could keep going with that if you wanted to. You say, all right, I know 270 degrees because I know the coordinates of these points on the unit circle. 0, 1, -1, oops, -1, 0, and 0, -1, right? So your points are of this form on the unit circle, right? Cosine x, sine of x, okay? Now for 45 degrees, we've just determined what those are going to be. So I should know 45 degrees. I should be able to kind of determine what the sine and cosine are there, right? Sine and cosine are, but each, I guess, square root of 2 over 2. So square root of 2 over 2, square root of 2 over 2. Okay, and last time we even talked about how you can extend that reference angle wise to these different quadrants, right? Because they're going to be the same coordinates, they're just flipped, in x or y. It's either going to be positive or negative based on where it's at. So we know that a little bit. Now today, what we've come in here, we've kind of said, well, okay, I also know at a 30-degree angle and a 60-degree angle, right? So your 30-degree angle, right, is what we talked about earlier. If you come into your 30-degree angle, your sine we said was 1/2, so that made your cosine, and we'll discuss this in a little more detail, square root of 3 over 2. 60-degree angle is kind of like those, but it's flipped, right? It's 1/2, square root of 3 over 2. Okay, so now we're kind of building up all these kind of angles and these points that we know. My advice is to practice this a little bit, especially if you're using triangles, to kind of be able to draw these triangles and kind of remember the lengths of these sides. So, for example, when I'm trying to figure out something that's got a 45-degree angle in it, I can kind of, let me redraw that. If I come in here to a 45-degree angle, my monitor keeps moving. I kind of draw it in here like this. Right? I have a triangle. Here's my pi over 4, 45-degree angle. I know the shortest side on any of these triangles is going to be 1. So if that one's 1, this has to be 1. This is square root of 2. If I wanted to draw a 60-degree angle, I would come in here and say, all right, that's a little bit different angle. So that's my 60. That's my pi over 3, or 60-degree angle. Shortest side, guess what? 1. My longest side in this case is 2, so I remember that this other one is the square root of 3. So I just need to know those measures. And really, that's all you need. But you can also come in here and say, well, what about a 30-degree angle, right? So it's kind of the same deal because this one is our 60-degree. So if I come in here for a 30-degree angle or a pi over 6 angle, short side is 1, the hypotenuse is 2, and then there's your square root of 3 side. So you should be able to use these triangles now to come in and figure out what these sine, cosine, tangent, etc. are. And we'll practice that a little bit more. There are actually some other shortcuts or other methods for remembering these, and I'll show you those probably in the next section. But we're at about 30 minutes, so I'm going to move on. Now, two angles are considered complementary angles, complements, if their sum is 90 degrees. In degrees, if it is in radians, it's going to be pi over 2, right? They're equivalent. So if you look at this triangle here below, it's a right triangle, notice that I have theta and I have my 90-degree angle. So my other angle, if I take 180 minus that 90, it's 90. And I get 90 minus this theta, and that's going to be the length, or I guess the measure of my other angle here. So you've got three angles. You're going to have theta, you're going to have your 90-degree angle, and then you're going to have 90 minus theta. If you're doing it in radians, it'd be theta, pi over 2, and pi over 2 minus theta. So here it says find sine theta. Well, all I have here is letters, but as I look at theta, I say, well, sine of theta is opposite, which is A, divided by the hypotenuse, which in this case is C. So next I say, well, let's go flip up here to the cosine of 90 minus theta, so our other angle up here. Well, the adjacent side to that angle, not the hypotenuse, is A. And guess what? The hypotenuse is C. So it's the same thing. So the sine of theta is equal to the cosine of 90 minus theta. So you can use those cofunctions. Sometimes that's kind of neat. I don't use those a ton, but you can. So as an example, it says find a cofunction with the same value as the given expression. So sine of 46 degrees is the same as the cosine of 90 minus 46 degrees. So it should be the same as the cosine of 44 degrees. Okay. If I look at the other one, cotangent, notice how these work, right? Tangent and cotangent are co-functions. Same with sine and cosine. Secant and cosecant, they're co-function identities. So cotangent, I'm going to use tangent. So I'm going to say, well, that's the same as the tangent of pi over 2 minus pi over 12, right? Because it's in radians. Well, I need a common denominator. So I'm going to come in here and say, well, pi over 2, if I want that to be a common denominator, I need to multiply the top by 6 and the bottom by 6. All right? So multiplying by 1, not changing anything. So that's really the same as the tangent of 6 pi minus pi all over your common denominator of 12. So you get tangent of 5 pi over 12. Okay, so that's just kind of another way of representing those. One last thing that I want to kind of point out on here, a couple examples here, but we'll probably just do a couple of these and the rest I'll review in class, in an actual in-person class session. So it says many applications of trigonometry involve an angle made with an imaginary horizontal line. So that sounds a little weird, but it's really not as bad as it seems. So an angle formed by a horizontal line and your line of sight above the object is called an angle of elevation. So there's an example here, right? I've got a platform, a surveyor's platform, and we're going to say it's 5 feet up. So from that 5 feet up, if I were to draw a perfect horizontal level line from that line of sight, and I also sight a point that's above where that is, that angle here, 24 degrees as it's given, is considered an angle of elevation. If instead, here I've got this platform, and instead, here's my horizontal. If I'm looking kind of down, that angle is called an angle of depression, right? Because it's going lower. Okay, so here's an example. It says, sighting the top of beautiful Lane Stadium, a surveyor measures an angle to be 24 degrees. The transit, or the measuring platform, is 5 feet above the ground and 300 feet, should be feet, horizontally from the base of the stadium. So we can kind of see this here. It's all drawn out for you here. So I'm really looking for one thing, and it's kind of tricky, but really what we're looking for is the height of the stadium, right? So we're looking for this height right here. Now, that's what I want to find. Now, notice that my height is not necessarily exactly based on this triangle. If you look at this triangle, I can find that length. We'll call that x. We'll call that red part x. So I'm going to say, well, my height is going to be that length plus that 5 feet. That's how high this surveying station is. So x plus 5. So I'll come back to that. Now I can figure out though what x is, and it's all based on this triangle. So if we come in here and look at this triangle, we have an angle 24 degrees. We have an opposite side. We're letting that be x. And we're saying our adjacent side is 300 feet. So I have an opposite side and I have an adjacent side, not a hypotenuse. I have a representation of an opposite side. So I want to know that opposite side. And I'm looking at opposite and adjacent. To me, that's saying, hey, that's TOA, that's opposite adjacent, that's tangent. So I'm going to come in here and I'll say, well, based on trigonometry and my functions here, the tangent of this 24-degree angle has to equal my opposite side, which is x, divided by that horizontal, that adjacent side here, which is 300. Okay. So the question is, well, what is x? Well, I can find that, right? The tangent of 24 degrees, hopefully we can find. And if we multiply both sides of this equation, actually I'll change colors again. If I multiply both sides by 300, these 300s are going to cancel out. And I'm going to get 300 times the tangent of 24 degrees. That's going to be equal to x. So let's find that. Let's pop open the calculator. Give me just a second here. And remember, make sure you are in degree mode in this case because it is a 24-degree angle. So if I come in here and say, all right, 300 times the tangent of 24, I was all right, 24, and I'm in degree mode, so trigonometry tangent. So is this number, and I want to multiply that by 300. So times 300, and I get 133.57. So I'm coming here and say, all right, x equals 133.57. Now that is x. Remember, that is not the answer because that's not the height of the stadium, because you still have to account for that extra 5 feet. So my height is actually that plus 5. So it's actually 138.57 feet. And I think that's fairly accurate based on some things that I looked up. But that's about the height of the stadium based on that surveyor station. You see that sometimes. So anyway, kind of interesting, kind of gives you an example of kind of how triangles and these measures and opposite and adjacent and all that are used. The last couple things I'll point out here says the next example says use your calculator to find theta where sine theta equals 0.866, because you're going to see this in the homework. It's not really covered until a later section. But the way you solve this equation is you actually take what's considered the inverse sine of both sides. So if I take the inverse sine of sine of theta, then that's what's going to give me theta. That's how inverse functions. F inverse of x is x. F inverse of f of x is x. So sine inverse of sine theta is theta. The sine inverse of 0.866, I don't know that. I'm going to have to use a calculator for that. And there's really a couple different ways you're going to see this. One is that sine inverse, sine -1 superscript there. Or sometimes you'll see this as a sine. Stands for arc sine, but it's actually the same function as inverse sine. So if I come in here and say 0.866, and I say trigonometry here, if I do this little second button, it brings up inverse sine, and I get 59.997. So I'm going to say it's about 60 degrees in this case. Now remember, this is in degrees, so use your degree symbol. If I did this in radian mode, I'll get a different answer, and I will accept either one, but just make sure you specify if your angle's in degrees or radians. And then the last thing I'll point out here, you see sine inverse, theta equals sine. It looks like sine to the -1 power, but it is not, right? This is not the same as 1 over sine of 0.866. Not the same value at all. It is inverse. It is not sine to the -1 power. Okay. It's a little confusing, especially when we did sine squared and talked about that a little bit last time. So anyway, you need to be able to do that on your calculator. We'll walk through that a little bit when I get back to class as well. The last one I'm going to let you do. It says the flagpole in the middle of Sesame Street. So I'll even kind of sketch it out for you. So I have a flagpole, and it gives you a height. I'll even draw a nice little flag here. And I don't know who's on there. We'll say we got a nice picture of Elmo on here, right? So there's his nose. He's got a mouth. We'll pretend. So there's our flagpole. It says it's 14, I'm sorry. So there's our flagpole. It's 14 foot high. So there's our 14-foot high flagpole. The next thing says cast a shadow 10 meters long. So let's kind of come out here. So this shadow, right, it's not perfect, but we'll say everything's level ground here. We'll say that shadow is 10 feet long. It says find the angle of elevation of the sun to the nearest degree. So if I take this point, what I'm really looking for is this angle here. We'll call that alpha here. So you should be able to, kind of similarly here, you should be able to say, all right, here's my angle. This looks like a right angle. So what trigonometric function is represented here? So I have an angle, and I have two sides that are given. I'll give you a hint. It's not the hypotenuse. We don't have that. We have two other sides, right? Opposite and adjacent. So which trig function is going to give us that? And that should help you set up an equation that would help you solve this. So anyway, that's all I'm going to do for this section. Again, about 40 minutes seems to be about the length it takes me to get through these, so I apologize they're a little long, but you can, scan around as you need to. Otherwise, this is probably it for now. So we'll be back in class at the conclusion of this section. So starting in section 4.4 on Tuesday, the 31st of August, we'll be back in class starting section 4.4 after we review a little bit and stuff. So anyway, let me know if you have any questions. Otherwise, I'll see you next time. Thanks.